Hello everyone. In this video we will go through an example in which we will design a controller for a given system using the frequency domain method. The system which is provided for us is in the form of a transfer function with 10 over 1 plus s to the power of 2 as the describing transfer function. Now we want to first sketch the body diagram for LOS and design a controller such that the order of GC is smaller than or equal to 1, so we are going to design a proportional or a first order controller. Steady state error should be smaller than 1% for a step reference. The crossover frequency should be bigger than 1 radian per second. The phase margin PM should be more than 20 degrees. And for the noise attenuation, we need to have gamma n equal to 0.1 for frequencies bigger than 10 radian per second, and gamma d should be equal to 0.1 for frequencies smaller than 0.1 radian per second for the disturbance rejection. And then we will verify it using MATLAB to see whether the control that we have designed is satisfactory or not. So as the first step, we will consider GC of S as 1 and form L of S, which is equal to GC times GP, and it will be equal to 10 over 1 plus S squared. Therefore, L of J omega will be equal to 10 times 1 over 1 plus J omega squared. Drawing the body plot for this system is quite straightforward and easy. We have only 3 components in total, 10 and 2 poles at omega equal to 1. So omega equal to 1 will be the corner frequency. For 10 we will have constant value of 20 dB. As the amplitude, and in terms of phase it will give us 0 degrees. And then for 1 over 1 plus J omega squared, we have two indeed poles at omega equal to 1. For each one, we will have amplitude almost equal to 0 up to that frequency, omega equal to 1. And then we will have minus 20 dB per decade. And since we have 2 poles at that frequency, we will have, you would need to consider it 2 times. Therefore, in total, we can say that the amplitude plot for L of J omega will be equal to 20 dB until omega equal to 1. And after that, we will have indeed 40 dB per decade as the slope. So in 1 decade, we will have 40 decibels of change. So here we will have minus 20, and it will continue like that. In terms of the phase, for those 2 poles that we have, there will be at omega equal to 1, we will have minus pi over 4. 1 decade afterwards, we will reach minus pi over 2. 1 decade before, we will have almost 0. So this will be the approximate phase for one component. The one in blue will be the approximate phase for the second component. And in total, we will have minus pi over 2 at omega equal to 1 and minus pi after omega equal to 10. So this will be the approximate phase plot for this system. We already have the body plot drawn by MATLAB, and you can see that it is kind of quite similar to what we have over there. So phase amplitude starts from 20 dB at very low frequencies. The crossover frequency is here, which is omega equal to 3. It's almost, it might be exactly omega equal to 3, or it's close to omega 3 radian per second. And then we have minus 40 dB per decade. As the slope. In terms of the phase, we start at 0 degree. The phase decreases around omega equal to 1. At omega equal to 1, indeed we have minus 90, and then as omega moves towards infinity, we get minus 180 degrees. So what we have obtained here is kind of similar to what we have got with the MATLAB. Okay, so we will focus on that figure from now on. So we have the sketch of the body plot sketch of the system for L of S with GC of S equal to 1. And now we need to define the forbidden areas to see whether amplitude plot enters into those forbidden areas or not. For the forbidden areas, we'll look at the specifications here. For the noise, we have gamma n equal to 0.1. This means that amplitude of L of j omega should be bigger than or equal to minus 20 dBs for this range of frequencies. So let's go and show it on the omega n is equal to 10 radian per second. So for 10 radian per second, we need to have the amplitude bigger than minus 20 decibels. So this will be our dangerous zone, the one that I'm highlighting in yellow. And we can see that currently the amplitude plot does not enter into this dangerous zone. So even now, without designing a controller, we are happy with that. In terms of the disturbance rejection, we see that we have gamma d equal to 0.1 for the frequencies smaller than 0.1 radian per second. This means that we would need to have amplitude of L of j omega bigger than or equal to 20 decibels, plus 20, for the frequencies smaller than 0.1. And now we will show it here. For the frequencies smaller than 0.1, which is this frequency, this will be the dangerous zone for the disturbance rejection. And now we can see that the amplitude plot is just on the border. Yeah? So to satisfy this requirement, we would need to move the amplitude at very low frequencies a little bit upwards at least, in order to have the desired disturbance rejection property. Then we can check the steady state error requirement. We need to have steady state error smaller than or equal to 1% for a step reference. Currently we have a type 0 system. One way would be to add an integrator and create a type 1 system in which the steady state error would become equal to 0. Another way would be to have a type 0 controller such that the whole system remains as type 0. In this case, we would need to have the generalized gain for the controller to be bigger than or equal to 10 in order to satisfy the requirement on the steady state error. So if we have generalized gain bigger than or equal to 10, then the steady state error will be smaller than or equal to 0.0099, which is smaller than 0.01. So that's what we might do. Yeah, we can continue with designing a type 0 system with the generalized gain bigger than or equal to 10. And then the requirement on the steady state error will be already satisfied. The simplest controller to pick is a proportional controller then. if we have a proportional controller with GC of S equal to 10, the amplitude plot will move upwards by 10 decibels, by 20 decibels. If GC of S is equal to 10, I'm going to draw the new amplitude plot with GC of S. If I say GC of S is equal to 10, then the amplitude plot will be shifted by 20 decibels upwards, and as a result we will obtain the new amplitude plot somehow like this. So this will be the resulting amplitude for the L of j omega with this controller. What happens here is that we will be fine with, in terms of the disturbance rejection, we will be fine in terms of the steady state error, but now we have the part of the amplitude plot entering into the dangerous zone for the noise attenuation. So this is not a good solution indeed. Yeah, we cannot use this. On the other hand, the crossover frequency will also increase. It will move to maybe around 10 or even more than that. It will be 10 indeed, almost. And at 10 radians, the phase margin that we will get will be quite small. It might not even satisfy the requirement on the phase margin, which should be bigger than 20 degrees. So using the proportional controller with the gain of 10 is not a good solution. Therefore, we will go for the first order controller. By looking at the body plot that we have here, the best scenario would be to increase the gain. Let me clean this. The best scenario would be to increase the gain at low frequencies So we have a gain of 10 at low frequencies, and then make the gain of the controller 0 for the higher frequencies. In this case, the steady state error requirement will be satisfied. Crossover frequency will not move. It will remain as 3 radian per second. And the amplitude plot will not enter into the dangerous zone for the noise attenuation. And we will be happy with all the requirements, hopefully. And looking at this kind of controller, you should think about using the lag compensator. Because if you remember, for the lag compensator, we have this kind of frequency domain behavior. The amplitude at low frequencies is a given value, then it goes back to 0. At high frequencies, it will be 0. And in terms of the phase, we will have some negative phase injected to our system. But if this negative phase is injected at low frequencies, let's say it is injected around this frequency here, and if you add it to the whole frequency of the system, we might end up with a frequency, a phase indeed, plot for the system similar to this, which is okay in terms of the stability. Nothing special is changed here because we are far from the change happens far from the crossover frequency, which is 3 radians per second over here. Alright, so then for our lag compensator, we will use the generalized gain equal to 10. So that's what we are going to do. We only need to improve the steady state error compared to a proportional controller where GC of S is equal to 1, because all the other properties are okay. And similar to the root locus approach synthesis of the controllers, we will use we would need to use a lag or PI controller in order to improve the steady state error. And we are going to pick the lag compensator at the first step. For our lag compensator, we will define it in this way. We need to have the generalized gain equal to 10. The pole and 0 of the controller are selected at minus 2 times 10 to the power of minus 2 and minus 2 times 10 to the power of minus 1. Indeed, here we have the pole and 0 of the controller. 0 is at minus 0.2 and the pole is at minus 0.02. And the generalized gain for the controller is 10. You might wonder why these values are chosen. First of all, we have the relation between these two. The ZC over PC is equal to 10, 0.2 over 0.02. And this is equal to the generalized gain, GC tilde, which is also equal to 10. If you go back and check the video that we have on the properties of the lag compensator, over there we had the low frequency amplitude equal to 20 logarithm of alpha. And we wanted to have this equal to 20 dB, or this would needed to be 20 dB. So alpha is chosen as 10. And alpha also determines the relation between ZC and PC. So we need to have this relation between the 0 and the pole. And why we have chosen 0.2 and then obtained minus 0.02. This is because we want to have the pole and 0 of the controller being at low frequencies. Yeah. First of all, we should be somewhere smaller than 10 decays is smaller than 3 radian per second, which is the crossover frequency. So we would need to choose some place smaller than 0.3. And on the other hand, the change that the amplitude plot that we want to move upwards should also happen after this 0.1 indeed. So if I want to give you an example, we wouldn't want to have the amplitude for the controller being like this, because in this case this area wouldn't move upwards, and therefore we will have problems in terms of the disturbance rejection. And on the other hand, we wouldn't want to have something similar to this as well. So we wouldn't need to have this kind of lag compensator, having the zero of the controller at high frequencies, 0 and 1, because in that case the amplitude plot would move upwards, the crossover frequency would move towards the right side, towards bigger values, and as a result the phase margin that we would have obtained would decrease as well. So therefore the frequencies for the 0 and pole of the system of the controller are chosen considering this, to have the corner frequencies 1 decade, let's say, is smaller than the crossover frequency, and also to have them bigger than this 0.1 radian per second for this example, because we want to increase the amplitude at frequencies lower than that. I hope it's clear how the values are chosen. However, this is one solution. You could eventually have chosen 0.23, for example. It would be also acceptable. In that case, dividing it by 10, you would get the location for the pole at minus 0.023. This should also work. They are not that different than each other. And you should also remember that designing the controller, you will not end up with a unique solution. So there are multiple solutions which could be valid. Having that controller, now we can check whether the phase margin is satisfied or not. So our controller will look like this. Yeah? If we have the pole and 0 at the given positions, the controller at the end will look like 10 times 1 plus 5s or 1 plus 50s. Now let's check the phase margin. The phase margin will be obtained at the frequency in which we have the amplitude equal to 0 dB or 1. So this is the omega equal to 3. The 3 radian per second is the crossover frequency. At that frequency, we can calculate the phase of L of j omega, which includes the controller and also the plant itself. So these two terms are from controllers, GC, and this term comes from the plant itself. And if we plug in the values, we will end up with the phase margin, which is 33.41, and it is bigger than 20 degrees. So we are happy with the phase margin as well. And as a result, the lag compensator that we have designed satisfies all the requirements. Over here in this figure, you can see in blue the original system with GC of S equal to 1, and in red we have the system with the lag compensator. So it's this one. You can see that for the high frequency range, the amplitude remains almost the same. The crossover frequency remains the same, which is 3. In terms of the amplitude at low frequencies, you see that the amplitude at low frequencies is increased indeed by 20 decibels. As a result, the steady state error requirement is satisfied now. The amplitude plot doesn't enter into the dangerous zone for the disturbance rejection and also for the noise attenuation. So we are fine with that. And in terms of the phase margin, now the phase margin is a little bit decreased to 33.4 was, yeah, is now the phase margin. It's a little bit decreased compared to the case with the GC of S equal to 1 compared to the proportional one, but still it is fine. So we are fine with all the requirements. All of them are satisfied. As another option, let's also look at the step response of the system. This is the step response for the closed loop system. We have in blue the step response for GC of S equal to 1, and in red we have it for the lag compensator. You can see over here that when we have the lag compensator, the steady state error requirement is satisfied, while without that we have a bigger steady state error, which is not as we wish. In terms of the other requirements, over here we don't see the noise and disturbance rejection, but we can check the transient requirements. We had them in terms of the phase margin and omega c, but over here you can see how the introduction of the lag compensator changes the transient behavior of the system. The rise time remains almost the same. Overshoot increases a little bit. This is because the phase margin is decreased a little bit. And in terms of the settling time is also increased. By the introduction of the lag compensator, we have a bigger settling time. And I hope you remember this from the root locus approach. Over there, when we had the PI controller, or even with the lag compensator, the resulting settling time would be bigger than using the proportional controller. And that's because the closed loop system will have a pole which is pretty close to the origin, and that behaves quite slowly. As another solution, we could choose the PI controller. If we use a PI controller, the type of the system will increase by 1. We will have a type 1 system. The steady state error for the step reference will become 0, and GC tilde, the generalized gain of the controller, will become a free parameter for us. For the PI controller, we can set GC tilt equal to 0.1, and then we add a 0 at minus 0.1, and we have a pole at the origin. By choosing having the 0 at minus 0.1, for frequencies bigger than 0.1, the body diagram will remain approximately the same for GC of S equal to 1. So for our controller, for the new controller that we will have it in the form of 0.1 times 1 plus 10 S over S. If I draw the body plot for the controller itself only, for the controller itself, after omega equal to 1, we will have 0 dB, and before that we will have minus 20 dB per decade. And in terms of the phase, we'll have minus pi over 2 for the pole at the origin all the time. The next term would be at omega 0.1 we will have pi over 4, then we will have pi over 2, and now we need to add these two to each other to obtain the overall phase, and you see that it will be like this. So the amplitude plot after 0.1 will remain almost the same because we are adding 0.0 dB. In terms of the phase will get a little bit smaller, but after omega equal to 1, which is the crossover frequency, and around it, the injected negative phase will be negligible. So this whole thing for the PI controller, the location of the 0 and the generalized gain over here are chosen such that after omega equal to 0.1, the amplitude for the PI controller becomes 0 dB. Now we can look at the body plot and check whether all the requirements are satisfied or not. We can check the phase margin. It will be calculated around the frequency of 30 radian per second as the crossover frequency. And after doing these calculations, we can see that it will be obtained as 34.97 degrees, which is acceptable for us. Over here in this figure, you can see the body diagram for the original system with GC equal to 1 and for the system with the PI controller that we just designed. In terms of the phase margin, they are almost the same as each other. The crossover frequency remains also the same. At lower frequencies, you see that we have the injection of some negative phase, but it is okay for this example. It doesn't have any side effects. The system has become type 1, so the steady state error requirement is satisfied, and the amplitude plot doesn't enter into the dangerous zones for the disturbance and noise rejection. So the second controller that we have designed here also satisfies all the requirements. Any of them could be indeed chosen. Over here we have the step response parameters. The step response is shown, and we can see the step response parameters. In blue we have it for GC of S equal to 1. In red we have it for the PI controller. With PI controller, you see that the steady state error is equal to 0, so it satisfies what we were looking for. In terms of the settling time, we will have a bigger settling time for sure with the PI controller introduced. In terms of the overshoot, we will also have a bit bigger overshoot because the phase margin that we have is a little bit smaller, and the rise time is almost the same as the the system with GC of S equal to 1. Alright, so I think that's all for this video. I hope you have learned how to design the PI controller or the lag compensator for a given system in order to satisfy the requirement. The whole thing here is to change the shape of L of j omega's amplitude and phase whenever needed, mostly the amplitude. Thank you for watching and see you in another video later.